All right, good morning, everyone. Thank you for that great introduction by Joyce. Such an honor to be here today. We were talking last night about a couple things at dinner. The Matt mentioned, 8th annual Q2B here in Silicon Valley, so it's great to be here. AFRL has been part of this. I think this is our 7th year, and we've been a sponsor for several years now. We always look forward to it. We were talking last night, kind of comes Thanksgiving, Q2B, and then the holiday season. So, we look forward to every year. We have a booth here as well, so I encourage folks to stop by, talk to our subject matter experts who are there, and you can get some more insight into what we are doing at AFRL. So let me jump into it here in terms of what we're doing and how we're looking to invent the future for the Air Force at the Air Force Research Laboratory. Let me level set it to begin with in terms of quantum information science around AFRL. But before I jump into the QIS part, let me just spend a few minutes on what AFRL is. So we are the research and development arm for the Department of the Air Force. The Department of the Air Force encompasses both the Air Force as well as the Space Force. So you can see it on the slide there in terms of a lot of space opportunities that we work on. But AFRL encompasses a total of about 11,000 employees. About 6,000 or so are government employees, another 5,000 on-site contractors spread out among 10 different geographic sites, working on a wide array of technologies at 10 different technology directorates. Myself, I'm part of the Information Directorate. I'm the Deputy Director in Rome, New York, working for Colonel Greg Stevens, whereas quantum is one of the primary areas that we do work on at the Information Directorate. But really looking at broader AFRL in terms of quantum information science, of those 10 technology directorates, 6 of those are working in different areas of quantum. I'll break it down later on in my next chart as to what those 4 primary areas are. But if you just look through, and I won't spend time going through that, but basically the Information Directorate in Rome, we're working on quantum computing and quantum networking, which actually forms the basis of most of my talk. But really, as I talked about last year, a lot of great work is going on elsewhere in AFRL, specifically in the sensing and timing arenas, as we look to be able to operate and function in GPS-denied or corrupted environments. And that work is primarily done at our Space Vehicles Directorate down at Kirtland Air Force Base in New Mexico. Also work being done at the Materials and Manufacturing Directorate in quantum sensing, as well as some supporting devices at our Sensors Directorate as well. Basic research, key to all this, we're going to kind of trace through some of that and how important it is as well, really being led by Dr. Grace Metcalf at AFOSR in Arlington, Virginia. And then finally, as we kind of wrap around this and organize and develop our quantum strategy, which has been online since 2018, we have a senior scientist, Dr. Kathy Ann Soderberg, who was named to that position last year, coordinates the research across the lab, as well as myself as I work on strategic partnerships. So you're going to hear a lot of that throughout this talk as well. And then last but not least, our international sites. We have 5 international locations. So as we look at the global ecosystem, especially in quantum, we can't go at it alone. We really need those strong partnerships. These 5 sites work as tech scouting offices for us, really funding basic research, academic outreach. And then as those technologies are promising or even maturing, we can pull them inside into the laboratory as well. So that's how we set the background. Now, what do we envision quantum doing for the Department of the Air Force? And as I mentioned, both Air and Space Force. So I've shown this chart in the past. It's time tested. We tend to update it, as needed, but it's really, lasted throughout our quantum strategy as we develop this. First thing to highlight is in the upper left-hand corner would be, how we're looking at a breakout of our program. I mentioned those 4 key areas for us. So there we're talking timing, sensing, computing, and networking. If you look at the main areas in those 4 circles, they're interconnected by supply chain, workforce development, as well as other fundamental technologies that really link these all together and form really this kind of not only endless research and development loop, but deployment as well. And then when we think about deployment, Timing and sensing are our nearest term applications, probably no surprise there, especially as we look to operate. And again, as I mentioned, GPS denied and contested environments, but you see the color codes there. We're really talking in terms of timing, developing better clocks, more accurate clocks, and not only that, but size, weight, and power with those clocks as well, those clocks that would need less frequent updates per day. And you think about then being able to operate in environments that we may be asked to operate in. Bringing those together with sensors, so things like accelerometers, gravimeters, gradiometers, magnetometers, all key devices that when you put the clocks together with those devices, the appropriate architecture, ideally you'll get to being able to operate and provide capabilities for a long duration, unaided inertial navigation that our systems will need to operate in the future. Networking and computing, longer term technologies, on the order of, depending how you frame this, it was an excellent talk by IBM, kind of with Oliver just framing where we are in the state of the industry right now. But you think about, maybe 10 years or so for a fully quantum corrected computer, as we like to phrase it, cryptographically relevant quantum computer, as well as maybe networking technologies that we see deploying hopefully within 5 years or so. There we're really going to fundamentally rely on property called entanglement. So we'll talk a lot about that as we go through, but the capabilities that those then provide are certainly secure communications, low probability of intercept communications. Here I'm talking about really moving beyond quantum key distribution and really looking at entanglement distribution. Ideally tying together clocks, sensors as well with that network. And then finally on the computing side, we'll talk about some specific problems of interest, but really providing a decision advantage to our warfighter with those new capabilities that quantum computing will enable. I talked about, kind of that loop in research and development. Here I'm really showing it. We're very proud of this in the fact that we're able to go from basic fundamental physics. You see it there with the cold atom, understanding those physics levels, probably lots of funding at the university level with what we call fundamental or 6.1 research, 6.1 research. Moving on to lab type of development. Here we're showing a cold atom atomic clock. That's a picture from NIST, the great work that's going on at NIST. Those systems aren't deployable though, right? So as we think about moving from the lab to the field, we really need to think about swap, size, weight, and power. How we can take those lab type of experiments, move out into the field. If you recall last year I talked about some experiments we had done at RIMPAC. So very critical as well, really thinking ahead to that, to be able to get to something rack mounted or smaller. But then how do we continue to bring in that research and development piece? So here I'm showing some very critical work, and you're going to sense a trend in this talk, but really integrated photonics. And we see just huge opportunities for integrated photonics as it continues to mature, as we're working with partners such as AIM Photonics, which I'll talk a little bit more about, but really allowing those technologies to go from basic fundamental research to the lab, to something that's scalable that you could bring out to the field, to something that is very much deployable. And that is our ultimate mission. Now let's dig into the last 10 minutes or so, specifically networking technologies. I have the next 3 slides set up on what we're doing in quantum networking. So you can see the capabilities enabled there, really being able to distribute entanglement between a multitude of nodes, multiplicity of nodes, significantly advancing timing, sensing, as well as ultimately computing. We certainly see probably computing being, an initial application area where we'll be able to tie together multiple modules for quantum computing systems. State of the art, no surprise in terms of what's being done around the world. So for a good example there is certainly what China's been doing. We've read a lot about that. Netherlands as well, some great work being done in the Netherlands in quantum networking. We're currently working on an agreement with the Netherlands that we hope to have signed in the coming months or so. But let's look at AFRL research. So as we look to develop quantum networks, we're really developing a heterogeneous network. By that, I mean 3 different qubit technologies that we're working on, bringing them together. The first one, as I've already mentioned, and as I said, you're going to sense a theme here, integrated photonics for information transmission and processing. Now, if we incorporate quantum memory components into this, specifically we're working on trapped ions there. Ytterbium-based systems was something we worked on initially, and now we've moved on to barium systems as well. We bring those together, Three disparate qubit technologies. You might wonder, well, how do we move between them? We really need transduction, be able to frequency translate between those types of systems. So that's something where we're really pouring a lot of effort into, is being able to realize those transduction technologies. We've had some excellent results, being able to go in the superconducting regime from optical, or from microwave onto optical carriers as well. Looking at larger picture, so that's work being done at AFRL in Rome, New York. The daytime quantum communications, we're using filtering and adaptive optics. This is being done at our directed energy directorate in Albuquerque, where we're looking from ground to space type of systems, also working with some international partners in that arena as well. You know, one of the big things that we really stressed on that early fundamental to fielding capabilities is taking early looks and really thinking engineering-wise what's going to need to deploy those technologies. So we have some drone work under development at our Innovari Advancement Center, where we're doing actually quad, hex, and octo rotors. So here we're using an octo rotor for actually putting an ion trap on with our partners at Inflection. Being able to distribute that signal. So we've done some initial work on that, and we're going to continue to build upon that, ultimately distributing entanglement and folding in integrated photonics there as well. Now let's spend the next two slides. I really wanted to really foot stomp the work we've done in our past year in deploying fiber-based networks, classical type networks with quantum signals enhanced and overlaid upon those. Oops, let's see. On this diagram right here, really the credit goes to Dr. Aaron Sheridan for really being the architect of this. We've done an in-house, in-laboratory type of network where we've done a kilometer-based network as well as 100 meters or so, just kind of scaling that up. You see a ring-based network there. Really leveraging what's been done in industry for several years now, coarse WDM as well as dense WDM technologies. We then have pushed that out. You can see in the diagram there, kind of the looking down at Innovari and our deployed fiber loop, two loops, 10 kilometers and a 5 kilometer loop. Measure the loss there. Typically what we get is around 6 to 7 dB, so very typical, what we might expect. Here in this network, you know, we're now looking at, and I'll show some results on the next slide, how we can actually start incorporating some of those different qubit technologies. So I already talked about our superconducting qubit nodes, trapped ion nodes, as well as obviously tying that together with our integrated photonics, and then really leveraging and picking up the transduction technologies that we've been working on. So some results here, some quick results as we've deployed that. So first thing, you know, we've noticed as we've sent signals out, Aaron likes to always point this out, is that, you know, being out in the field is much different than being out in the lab. So actually, as we've gone through, apologies here, this jumped ahead on me. As we've gone through this, you can actually pick up vibrations and you know, upstate New York, get a lot of snow, snow plows come by. You can actually see disruptions in the fiber. So we're working hard on, you know, overcoming those types of disruptions. Some examples there where we've actually sent entangled photon pairs through. This is a chip designed by our in-house researchers, fabricated by AIM Photonics, or American Institute of Manufacturing of Integrated Photonics, one of the DoD's manufacturing institutes. 4 outputs from that, spontaneous 4-wave mixing that comes out of that. So we're entangled in both the frequency domain as well as the polarization domain. You can see some of the experiments there, some of the results from those experiments. So cross correlations at about 45-second or so time differences, and then the copolarization central peak that you see there, really with the co-correlation there with the strongest signal. So we've demonstrated that we can send out those quantum signals across a multitude of wavelengths corresponding to, you know, basically the coarse WDM types of wavelengths and the spacings there. And the fact that we're able to survive, send those entangled photon pairs through the network, and they're able to survive. Next steps will be fidelity of that quantum network. Here I'd also like to point out, you know, again, you're going to sense this, and certainly it's part of my job, the partnerships that have enabled this. We're working with many partners, so strong in-house team at AFRL, but also working with partners such as QNect and APC, or Automated Polarization Controller. We just installed that in our network. That came through an Air Force SBIR program, which I'll talk a little bit on an upcoming slide. Aliro, great partner as well. We've also been working with IonQ on setting up quantum nodes within our laboratory, and we have one node going right now. We're expecting, it was announced recently, you could look back at press releases, on a 2-node system that'll be coming very shortly as well. So great partnerships there. We're expecting to announce some more in the future as we continue to really grow what we're developing in Rome, New York. And the computing side, so just briefly touch upon this. We don't develop quantum computers in-house at Air Force Research Laboratory, but we really leverage what's being done out there in the commercial world. So shown in the bottom blue box, 2 primary partners for cloud access for us, IBM and IonQ. We've been working with IBM for over 5 years now. IBM systems, you can see the number of systems that we've accessed there. It's been great, not only for our in-house team and our in-house researchers, but also our external researchers as well, that I'll talk about some of the partners that we bring on board working with them. IonQ, working with them on their trapped ion system and having access to it now, really allows us to explore different modalities and how things operate on those different types of systems, something our scientists and engineers are really excited about. We're hoping to expand this, have other access points in the future as well. Things that we look at from the computing point of view would be our involvement. So I mentioned we don't develop the actual hardware or build a system, but we do evaluate hardware. We do test and evaluation for DARPA under the US2QC program, the QBI program, Quantum Benchmark Initiative, which it's morphed into. Been a great program for us to really get involved in it. We formed a new team. We've been able to hire 5 government scientists and engineers. We're going to expand that as the program expands. We're really serving as an arm for DARPA, looking at what systems will scale and become practical in the future. The algorithm side, I'll jump to the next slide here as well in the interest of time. You can see the applications that we're looking at with our partners through these cloud-based systems. But really bringing government agencies together. Really would like to highlight the Navy. Not just Naval Research Lab, but other parts and arms of the Army as well, looking at things like corrosion and how we can better understand that as they apply that to certainly the ships that are out there. Academia, industry, our international partners, so key for us. 3 main areas that we focus in on there would certainly be logistics, supply chain, how to optimize over those types of regimes. Very key for us, very hard problems. How to enhance machine learning, training techniques using quantum systems, very active area of research for us, and certainly quantum simulation, quantum chemistry, molecular modeling, developing new, better types of materials, very much of interest for us. As systems come along, certainly things like weather forecasting, cybersecurity are going to be very much of interest for the Air Force, but certainly we've jumped in early. We jumped in over 5 years ago with IBM. We're continuing to grow that with our team because we see a real future, certainly, for quantum as the systems development. Enabling technology is very key to us here as well. Won't spend a lot of time on this, but certainly, as we look to go from lab to field to deployment of these technologies, we're going to continue to need to push on things. I've already talked a lot about integrated photonic circuits and how critical those are to me. When you think supply chain, it always comes down to lasers and detectors, how to improve those, how to make those more rugged and compatible with things that we'll need actually out in the field. Diamond. So certainly nitrogen vacancy is key to us when we think of magnetic navigation and some of the work we've done. So if we move all the way on from the diamond substrate, beginning a very basic research, how to onshore those capabilities, to then next to the growth and the patterning, leveraging machine learning technologies that are out there to improve the efficiency of those devices. As we move it into systems now and subsystems, forming those into magnetometers, we've really seen some great improvements. There's been some nice Air Force demonstrations. Our materials and manufacturing directorate is working on that in-house. We've also done some external work with Sandbox AQ through an Air Force SBIR program. Been great to mature that technology. Also folds in some machine learning technologies to really remove some of the extraneous and extemporaneous signals that you would see from the aircraft as you're really looking at magnetic map matching and allowing you to know precisely where you are as well. How you connect with AFRL, I'm basically out of time here. Lots of opportunities, lots of great ways to connect through our small business program. I've mentioned some companies that have come through there. We did a quantum collider back in 2020 where we put out $40 million of research for that. Companies such as QNect have come through that. It's been great for us as well. Our Innovare Advancement Center, I encourage you to go to innovare.org. You can learn about the work we're doing there, how you can possibly collaborate with us as well. As I mentioned, our team will be here at our AFRL booth. I'll be here the next couple days. Love to talk to you more about it. And then just wrapping up, summer students, summer faculty, very big for us at AFRL. Here's a sampling of some of the work they do. We bring students in all the way, we start them early, certainly with the STEM camps, but then as we bring them on to interns, some as early as high school students, early college students actually being in the lab, running experiments, and ultimately publishing as well. And it forms just a great workforce pipeline for us as well. So with that, thank you very much for your time today. I think we're out of time. I'm not sure if there'll be time for questions, but look forward to connecting and talking to everyone more today and tomorrow. Thank you. There you go.
Thank you. We got one question. Is the AFRL interested in integrating quantum computing resources with HPC systems?
Yes, actually we are. So as you might imagine, the Air Force, AFRL, very much a leader in high-performance computing resources and what it could do for developing and enabling future technologies. The merger of that, I think, is going to be very critical. Certainly the architectures we see, certainly quantum computing is going to have its niche. HPCs will have its niche. Other systems, will continue to develop, but with the marriage of HPC and quantum, very much of interest to us.
Thank you, Mike.
Thank you.
Round of applause for